And welcome back. So let's move into the sequence of nodes and see what that's all about. In order to do so, we're going to need to define a new user-defined type, and we're going to create it as a struct node. It will have two data members, both of which will be publicly accessible by users of their class of our type, because by default, data members of a struct are public. So the first is going to be an integer object named data, and it will house some sort of integer object. Next is going to be next, which will store the address of a node. It is going to be a typed pointer to a node. So what is data, what is next, and how might these two members be useful to us? Well, let's go ahead and allocate a new node on the free store. And to do so, we're going to assume that I have already defined a parameterized constructor for node that will initialize the data field with the argument to the parameterized constructor and the next pointer with the null pointer. So in this case, we could create a new node, initializing its data field with the integer value of 7. The parameterized constructor would go ahead and ensure that the field next is initialized with the null pointer, as shown here, or represented here with the integer value of 0. Remember that new is going to return an address. This address is going to be stored in a pointer to a node that we will call head. And we'll see here it's going to be the head of the sequence. And remember, head's a named object. It resides on the stack. Let me draw this out quick. Okay, so up here, this is kind of what it looks like. So head is going to be a pointer to a node object. It's going to be pointing, so head will reside on the stack. The object to which it points, we see the new there, so it's going to reside on the free store. And we've set up that relationship shown in my wonderful drawing. If we want a perhaps more aesthetically pleasing way to think about this, we can say that head is pointing to this node object, whose next pointer is pointing to the null pointer, as shown with this yellow square with a X through it. So how could these things become useful? Well, because each node object has a pointer to another node object, we have the capability to string these dynamically allocated objects together in memory. What we're going to see here is head is going to serve as our entry point. It will give us the first node in this sequence of dynamically allocated objects. Once we get into this kind of sequence of nodes, we move from one node to the next, hopping around in dynamic memory by following the next pointers. So to get from, let's set this up first. So we have what we showed on the previous slide. Okay, cool. Now let's go ahead and say heads next. So that's making an assignment to that field. We're saying heads next is going to get the address of a new dynamically allocated node object. So it resides on the free store that's initialized, whose data field is initialized with 11. And we're going to store that address here. So this is before. Here's what's happened after. We can see here that the node pointed to by head is next field points to the null pointer. It's no longer the null pointer value. Instead, it contains the address of a node that's also on the free store. So what does this look like in memory? Let me draw it out. So notice here, to get into the sequence of nodes, we have to access it through our head pointer. Without head, we have no ability to access any node within this list of nodes. But if we do access it through head, notice that we can get to the first node within the sequence. If we want to get to the next node, all we have to do is dereference the address stored in that node's next pointer. And that will get us over to the next node in the sequence. And notice that this sequence of nodes is terminated once we reach the node whose next pointer is the null pointer. It points to nothing. So here's the node object pointed to by head. It's the first node in the sequence. we could get its data member, or we could also get the address stored in its next pointer. If we wanted to follow and get to the next node in the sequence, we'd go ahead and dereference this address here. The cool thing about these dynamic objects here is they're not laid out contiguous in memory. They're kind of scattered throughout the free store. So we actually have to jog from one to the next. It's not like we just simply offset over by some size like an array. They're not contiguously laid out. They're just each node object gets allocated where there is enough memory for a single node object. So we can follow that or dereference that address and then get at our next node within this sequence. And how do we know that we're at the end of this list or sequence of nodes? When the nodes that we're at has its next pointer, the null pointer. Okay, so before we move forward, one thing you might be asking about is what does head next mean? What's this arrow thing? Okay, if I wrote, let's say I wanted to get the address of, access this pointer here. So the pointer field of the node pointed to by head. If I were to write head, I have to dereference head because I have to get to this object here. I have to get to that object. However, in C++, postfix operators are going to bind tighter than prefix, which means that if I wrote it out as such, this would get evaluated first. And guess what? A head, so a pointer to a node or any pointer in general does not have a member named next. So this is not going to work. Instead, we would have to force order of operations with parentheses. And I don't think you'd want to do this every time. You'd have to say, I want to dereference head and use parentheses to show I want to get that object back first, the object pointed to by head, and then access that object's next field. The arrow is equivalent to writing that, and it's heck of a lot shorter because it's just head dash greater than sign followed by the name of the field or function that you'd like to access. And again, this notation here is going to be extremely convenient for us as we move forward. Okay, so what if I wanted to access the this object's data? What would be head data? Because again, this provides an address, so whatever's stored in that next field, this provides whatever is stored in that integer field. So if I wanted to add, say, a node to the end of some sort of list, how would I go about that? And the idea here is that, let's say, you know, it's a bit more there's a bit more depth to the sequence than just two elements. And what we'd want to do is essentially have to get to the end of the list and access the last node and then tag onto that. And that's what we're going to do here. So let's say that we're starting out with this here, what we created in the last slide. And we would like to add a node to the end of this list containing or storing the integer value of 8. Now, any of these like dynamic structures that we're going to be dealing with, there's almost always going to be a traversal involved in order to get from, say, our entry point to the point of interest within whatever sort of thing we're dealing with, in this case, a sequence of nodes. We cannot use head to move through this sequence of nodes because remember, head is our single entry point into the sequence, and if we lose it, we lose everything attached to the node that head was pointing to. So frequently we're going to create a new node pointer, and I'll just name it current node and initialize it with head. So at this point, you find a cool color, current node is going to point to the same node object that head does. And now what we want to do is we want to go through our nodes until we get to the last node. So if cur node is not equal to null pointer, we know that the list is not empty. If the list was empty, head would have been pointing to nothing. And therefore, we would have known that wherever we're attempting to add does not exist. We're adding to the end in this one. In that case, we would know that we're adding to the front of the linked list, which I have not shown code here for. So anyways, let's assume that we have at least one element before we move forward. So the next step is to actually move from node to node. So while cur's next is not equal to the null pointer, we're going to move from the node we're currently on to the next node. And we do that by assigning cur node the address stored in cur node's next. So we're going to take the value stored there and assign it to cur node, which will effectively make cur node point to the second node object in the list. Now at this point, our while statement is going to continue because because its conditional is now evaluated false. Notice here that cur node's next is pointing to the null pointer. That means we have arrived at the end of our linked list. And at this point, we know where we're going to hook on this new node to, or where we're going to attach it. So at this point, we can simply write cur node's next, allocate memory for a new node. In this case, it looks like we're going to have that node store the integer value of 8 and assign its address to cur node next. Notice that that is this field. It's kind of ugly. Let's right here, which means that we now get this cur nodes next. So that what used to be the last element in the list is now going to point to that node we allocated memory for that stores the integer value of 8. And it is in turn going to point to the null pointer because it is the last node within our list of elements. And we can kind of see this. Remember, each node is going to have an address. So this is the address to the first node within our sequence. We can see that the data in that dynamically allocated object is 7, and the address that it stores is the address to the next node in our sequence. That object is going to store the integer value of 11. And in its next field, it's going to store the address of the next node in the sequence, which is going to be that, storing the integer value of 8. Then finally, we're now at the end of the sequence of nodes, and we know that because this node's next pointer is the null pointer. So the next question is, can we avoid walking through the list? And the answer is yes. There's a far faster way to just tack on nodes at the end of the list. And that's going to be to not only maintain a node pointer whose value is the first node in the sequence, but we could create an additional pointer that's going to point to the last node in the sequence. This will require a bit of extra accounting because each time we're inserting into this list or say removing a node from it, we have to ensure that the tail is always set properly, and that is pointing to the last element in the list, and that the head pointer is also set correctly and always pointing to the first element in the list. Had we had this tail pointer in the previous slide is getting quite colorful, if we had this tail pointer to add the node storing the value of 8, not sure how this got by me, 8, all we'd have to do is simply allocate memory for that node. So we have a new node on the free store, store its address somewhere, in this case, a pointer, which I'm just going to call temp because we'll throw it away after this, and then say tails next. You're pointing to the address stored in temp, which is the address of that new node. And then we're going to say that tail is equal to temp. So how this looks is we have this new node. Oh, I guess it was 9, my bad. Continuing on from the last one, I'm sorry. So we have this new node with 9. Its next pointer is pointing nowhere. Tails next at this line is going to give us that pointer there, which we will set to temp. So that makes that connection. This line here is going to make tail now point to that object. Hopefully this is clear. I'm sorry about the confusion with the 9. We picked up where we left off, and this is the end result of this. And again, if you just run through these, you can see with the addresses that each, so once you get into the list, each node's next field is going to contain the address to the next node within our sequence. So this is the fun one. How do we add at a specific position? So what if we want to add at a specific position? So add in a node at some, maybe at slot as the second element or as the third element, whatever. So assuming this is the initial configuration here, we have a node of, or a sequence of 4 nodes attached together, each residing on the free store. So in order to add a new node at a specific position, we're going to need to walk to one before that location, provided that it exists, create a new node to house the data, and then absorb that node into our list. So the question here is, what if we want to add a node containing 7 at position 3? And if you're thinking about these as 0 indexing as an array, position 3 is where node 8 currently resides. So what we want to happen is we want to put this node, I think that actually should have said 12 in here. And we'll see that we need to essentially hook up some pointers to ensure that that happens. Let me pause this real quick. Okay, just made a couple updates to reflect the correct value that we're going to store in this new node that's getting added into our list at position 12. So what does that procedure look like? So we have to check and ensure we're not adding at the head of the list. And then we also have to accommodate if we're adding at the tail, because we have to ensure that those pointers are always set properly, that the head's always serving as our gateway into the list and the tail's serving as our immediate access to the last node in this sequence. So in this case, we're adding at position 3, which is going to be, we want it absorbed right between these 2 nodes, between the one storing 11 and the one storing 8. So how do we go about this? We know the position, and if it exists, we want this node to end up there. We want to accommodate adding at the head, so the first check is going to be, hey, if we're not at the, if we're not adding to position 1, that is the first at the head of the list, we'll go ahead and begin moving to the proper location. We'll initialize curd node to point to head. And then we're going to, as we mentioned before, go ahead and iterate, have some sort of iterative statement to move that pointer through the list to the desired location. In this case, how we need to hook things up is if we want this node storing 12 to end up between 11 and 8, in order to absorb it into the list, we're going to have to update the next pointer of the node who's housing this integer value 11. So our whole goal here is going to be to march to that node, which is going to be the node residing at essentially the index 3 less than the position, or the position that is 1 less the value we're looking for. So if this is a node at position 1, this is node at position 2, 3, 4, we need to get to position 2. Assuming 0 indexing, that would be index 1. So we hit this iterative statement, and for int I is equal to 0, I is less than position subtract 2, increment I by 1 each time we execute the body. In this case, we're going to hit the body of the loop, and we're going to move curr node forward. So cur node will now point to this element. At this point in the game, we are where we need to be to go ahead and absorb this create this new node storing 12 and absorb it into the list. So we'll jump out of our for statement because the conditional is no longer true. We'll create that new node and we'll have some sort of pointer pointing to it, which we'll call temp. Now we need to actually do this shuffling, and order of operations will matter here. If we were to point cur nodes next to this new node, notice that in that case, we lose everything that comes after it. So the way we need to absorb this into the list is first taking temps next and pointing it to the same thing that cur nodes next is pointing to. So notice how that's pointing to there. We need that to point to there. So we make this update first. So now temp, so now that new node we just created is pointing to where it should be. We need to now hook it up at the other end by pointing the node at position 2 to this temporary node. So we've done that step. Next step here, so erase a little bit, is to go ahead and take this pointer, cur nodes next, and point it to that node. And at this point, we have successfully absorbed this new node into the list, and we have formulated this. Notice here there are a couple of additional checks here. In the case we were adding at the last position, so at the tail end, and had a new tail arise from this behavior, we would need to update tail appropriately, but that's not something we need to worry about here. And again, if we were to be inserting at the head of the list, so replacing head with a new node, like maybe putting 6 at the front, and pointing it in that sort of way, obviously head would have to no longer point to the second element, but to the first. But that wasn't the example here. You can trace through that code on your own time. So the last part of this section, I know it's been a long one, is going to be the destruction. So we've dynamically allocated all those nodes. Can we just deallocate all the memory by writing delete head? No, we can't, because that would have only deleted the first node in the sequence. And actually, we'd have a huge memory leak and we would have lost everything else. So in order to destruct this sequence of nodes, we're going to have to traverse the list, visiting each and every node and invoking the delete operator on that node's address. This isn't as scary as it sounds, though. There's a pretty straightforward procedure to do this. We're simply going to make use of the head pointer along with an additional node pointer next, which will first be initialized to null pointer. So in the first diagram, we'll have this next pointer pointing to nothing. We're then going to get into a while statement, which will essentially read, while we haven't reached the end of the list, we're going to go ahead and assign the value of next to the next node in the sequence. We're going to call delete on the value stored in head, which in this first example will be that node's address, which will delete it. So notice in the second one, head's now pointing to something whose memory has been deallocated. It's technically a dangling pointer at this point, but we've at least returned it to the free store manager. And now we're going to go ahead and move head over to where next is. So next is simply preserving the next node in the sequence. Had we called delete on next, so if we just if we called delete on head, notice that that would have knocked out that node and we would have lost the address of the subsequent node in the connection. So that is why next is so critical here, because it is going to preserve this value here. That's its whole purpose. So that's why it's pointing to the next element in the list, because after we've called delete on head, we simply assign head the value of next and it moves us over. So now we're at this point. So next needs to be moved to heads next, and we set this up. And then we repeat the process. So this process will continue until the last node where the assignment of our next value will be null pointer, prompting the value of head to become null pointer after the last element is deleted. So you could literally have a while loop of the form while head, which is effectively communicating that while the head has a non-zero address, so while it's not pointing to the null pointer, continue to execute the body of the loop, which would do something like this. So a couple of observations about using this sequence of nodes compared against using our vector events. So when we have this string of dynamically allocated objects chained together in memory, one observation is that it's slower to retrieve an element from the sequence. We haven't explicitly showed this, but look, if we were searching or wanted the third element within this sequence of nodes, the only way to get there is through the entry point to our list, head. So we'd have to go from the first node, we pick a good color, from the first node to the second node to the third node to get to the third node. There's no direct access like an array where you can simply perform that arithmetic on the base address of the array and jump directly to that slot. The reason why you can't do that here again is because arrays are laid out contiguously in memory. Each integer object residing in it is kind of adjacent to the one above or below it. In the case of a sequence of nodes, these nodes are scattered all over the place in dynamic memory. So we actually are running from one to the other through its address. So that visiting process is not as simple as simply offsetting from, say, the address of head, because we have no clue where any of the nodes have had their memory allocated for by the free store manager. So it is, so that having to, and this is why I said all these operations for these dynamic structures, there's going to be a lot of iteration and a lot of traversing. So moving from one to the next to get to where you're going. However, the cool thing is that adding to this sequence of nodes is a lot faster. If we wanted to add, say, a node containing the value of 10 between the node 11 and 12, notice that all we have to do to absorb that into our sequence of nodes is point that node's next to that object, go ahead and take the node before it and point it to the newly allocated object. It's a traversal to get to that location, and then the assignment of effectively two values after the allocation of memory for this node storing the value of 10. Contrast that with the slow addition into the middle of sequence for an array, where you actually have to shift everything down before you have to make the assignment. Here we just have to get to where we're going, update a couple of pointers, and we're done. The other nice thing is that because these nodes are scattered all over the free store, they can grow as needed. There's no need to resize, because when we ask the free store manager for a node, they can put it wherever there's space for it. We don't need this contiguous chunk of memory as we did for the array. And one of the consequences of which, with that continuous nature, was that we had to actually get a whole new block of contiguously allocated items if we ran out of space. This is not the case for the sequence of nodes. We just request nodes on the free store as necessary and chain them up to one another. So as that ado, we'll go ahead and finish up here with a brief discussion on dynamic structures. I know it's been a long lesson, but this stuff is important to get through. So we're almost there.